welcome to Swarf and Chips. We have come to the Control Expo in Stuttgart, Germany to bring you some of the best technology we could find. There's German, Japanese, Italian technology on show, and also a little bit from Britain too. Car body panels need to be inspected because they need to be right. We've all seen older cars or slightly badly refurbished cars that got gaps in between all the little panels and of differing sizes, and it just doesn't look good. It's obviously not right. This is a way to inspect body panels, and it's brand new. This is the Poly Robot Automated Fixture System from Protos 3D. It's got a full GOM scanning setup to my left here. Look at that beautiful robot that can scan the whole part. But the interesting thing is they've got 6 robots here that can orientate themselves in any way to be able to hold on 3 points any kind of sheet metal part you've got. This is a fender, you've got a door card, you've got structural components, and you can change over to any of these kind of parts in less than a minute. Normally, manufacturers will be clamping down on the bolt holes with special fixturing that would take ages to change over between parts, but this can do it in under a minute. Now, you'll be thinking, actually, if they clamp down on the fixings, because that's what's going to happen when the panels are actually in the car, what they do here is actually quite special. They use some specialist Zeiss technology called virtual clamping. Now, since this is just sat on 3 points with suction cups, they actually take the component and they virtually simulate what's going to happen to the part when it gets clamped down. So you can just sit it on, you can measure it, simulate what it'll look like, and then make sure that it's going to fit absolutely perfectly. That makes a good looking car. Here on the Fixture Tech stand, they are making AGVs, and they've got an Audi V10 supercar here. This is not just to look good though, this is exactly how they inspect cars while they're half being assembled. At Lotus, they do the exact same thing. Now, these AGVs are all about moving the cars around the factory while they've been assembled, inspected, monitored, and this replaces what they used to use, which was a big crane and a fixture plate that would house the car so it didn't warp when they were trying to lift it around. And you imagine how much infrastructure you might need in your factory to have a big overhead crane and a big fixture plate, things swinging around. It's very awkward. Instead, with an AGV, you don't have to have any of the overhead infrastructure. You just drive the car from the start, assemble it on top of the AGV, inspect it on top of the AGV, and out comes a beautiful Audi supercar. I'm lucky enough here to be with Christina on the Kulza stand now. These guys do something very special. It's sample preparation for inspection of components. Now, Christina, what have we got here? Why would you want to take a sample of this?
We take an impression from the surface to make a roughness measuring with a tactile measuring with a tactile tool, or as well with an optical measuring tool.
Absolutely.
You can take both. And it's very easy, and you can fill in the impression material with this tube.
So we've got impression material inside the tube here.
Yeah.
This is going on the bottom face and the side face of the ground finish
Yes.
on a rack. This is all the teeth.
Yes, right. And you can reach regions which you don't reach with the normal measurement tools.
Because normally a tactile tool would be a flat thing that would drag along the surface, right? But you can't normally fit that inside the teeth here.
Yeah, that's right. And that's why we use this impression material. I gave it on the surface.
Absolutely.
And now I will cure it with the blue light in something around 1 minute.
And what is special about the material here? Does it have certain properties that means it takes a perfect surface finish of the component it's sat on top?
Yes, you can use this material as well in combination with this to bring your sample in the mold, for example. It's pretty easy handling, and you can. It's very flexible in your application.
Absolutely. And if someone was going to start using a piece of material like this, who maybe before they don't know how to inspect this, maybe they send it to the customer and hope it's correct. How do they start to use this? What equipment do they need? Is it literally single syringe and this?
They only need the lamp with the blue light and only the Technovate 2200.
Okay, easy as that. I love it. And now a minute later, we've cured the material, hopefully.
And then we will move. Maybe it will be helpful to have a tool like this.
To remove the material.
To remove
the moment
it.
of truth. And it's really hardened up, hasn't it?
Yeah, it's very hard.
So now you have to try and carefully remove it from the ground
very
surface.
Slowly.
Nice.
And you can see that will be solved from
there we go. It's cracked
from
up.
the surface.
Nice.
And you can see that we reach a very accuracy impression.
Brilliant.
And if you want to handle it in a better way in the measurement machine, you can bring it on a glass
on a slide,
and you with the same material. You bring a little of the Technovit 2210 on the surface and bring the impression in the right position and cure as well. Something around 5 seconds is enough.
Yeah.
And
perfect. Easy. And you're blinding me with that blue light. It's a very bright torch there. And so then you put this in an optical measurement device to measure like an Alicona machine or a 3D scanner to measure the full 3D surface of the material.
Whatever you want.
And you know that your rack in your steering rack in your car is correct, or whatever else you might use a rack for is going to have a perfect surface finish and have low friction in the gears. Thank you very much, Christina.
Okay. Welcome.
Sometimes you don't need to inspect a part all the way down to the micron level. You just want to know if a little component is welded on or if all the weld seams are on. Now, Jens, tell me, what have we got here?
So we are using augmented reality for visual inspection on a tablet. Like you just saw here, we're having the CAD file right now superimposed, that's what we call it with the augmented reality. It's superimposed on the welded part, the manufactured item itself. And now I can start doing like a visual quality control with a couple of functionality. To check if all those parts, features are existing and in the right place.
And we're seeing green lines here, which are the edges on the CAD file, and purple is the contours and the shapes and the forms on the CAD file.
Exactly. And we could also drill in something more special like those welding seams. We want to make sure that they are existing according to the CAD specification, like the inspection plan itself. And now you see you can really nicely visually look for all these welded seams and check if they're existent or, for instance, not. Like here in this case, they are missing.
So here you see them down here, they should have been welded, but it's actually not.
It's not. So I can start documenting and say, okay, that's not okay. I can do a quick classification also, like here, say for later purposes, can check, can say save and continue with my inspection.
Absolutely. So you can take a photo of the weld seam that's not there, send that off to management and say, look, this part is not wrong, there's something going wrong in the manufacturing process.
For instance, here it's just the wrong piece, they just welded on here because there is a lot of modifications to basically the same piece, and sometimes it happens that the technical drawing isn't just precise or it's hard to read it. So with the 3D comparison with the CAD file existing, you could tell here there's a deviation. You see with that hole and also with the shape. So once again, I can start documenting that there's some deviation here. Once again, say there's something not okay, save it. And once I'm done with my entire inspection, just to show, I get a full report that runs me through my inspection again. I can share, say with a supplier, if this is a piece I would use for further assembly and somebody supplied it and I can send it back and also instantly say, attach the report and say, okay, we found some deviation, we can't use this in further production. You have to make sure and do a remedy so that we have the good parts.
Absolutely, so it's not inspection down to micron accuracy, but it's absolutely reliable inspection for general weld seams, general components. Make sure your welded components or your manufactured components, like the one behind you, are absolutely bob on. We're back with Christina here on the Colza stand. This time we are taking an embedding of a component or material for metallographic testing in some resin. Now, Christina, while you're demonstrating to us how you take this embedding, what is metallographic testing?
Metallographic testing is a microscopic inspection of different materials.
Absolutely.
And in this case, we use odor-free material made out of powder and liquid, and can be mixed in a ratio of 2 to 1. And we fill in at first
Absolutely. So now you put in the liquid in first. It's kind of like an epoxy resin, like a hardener and a resin almost.
No, it's a special kind of.
Okay, it's very special. It's not epoxy.
Very special, not common. It's very new and it's odorless, and it's very
easy to use.
Easy to use, yes, and very quick.
Very quick.
Very quick as well.
You said previously.
For region control, it would be very nice because in something around 5 minutes, you have cured samples.
Yeah, absolutely. And you said previously previously, these kinds of samples would take a long time, and also the material you'd be working with would smell very bad as well.
Yeah, but
Almost like me after a long day at a show.
yeah, but these doesn't anymore. It's odorless. It's a special kind of modified plasticine, and so I fill in at first a little of these.
And we're putting it inside a standard mold here, and this is made for a certain machine that can take this size
Yes,
resin
it's
embedding.
much better, and it's as well as the protection of the sample as well. And I've given the sample.
Perfect. So this
Bring
is like
it
a
in the
copper
right
sample.
position.
Yeah. Brilliant. So you're putting the copper sample inside the resin here, and then you're going to pour
fill
some.
up completely.
Brilliant. So there's more going on top of this, and this is
And
so
now we
that.
have to wait 5 minutes, and everything's fine.
Okay, perfect. So the embedding will probably take 5 minutes to set. Let's go look at some more technology while we wait. Look at this, another fantastic piece of technology. This is computer tomography, also known as a CT scan. You might have heard this before. This is from Wenzel. This is a tabletop device. Now look inside there. On the left-hand side, you see the X. So what it does, it spits out X-rays from the left-hand side. Your component goes on top of the plate here and spins around. And then there's a detector on the left-hand side. And that basically what that can do is measures density and also geometric accuracy. Now, why would you want to do that? Well, components need to be accurate if they're going inside an assembly. So your functional faces are working, your bores, your faces, your flanges, your bore holes. But also, you want to know if your density is correct. So if you've got a cast part that may be plastic, injection molded, die cast, you want to know whether the density is correct, the porosity is there might be cracks in the casting, or holes or inclusions of different kinds of materials. This machine can do both those things, both dimensional accuracy and also material integrity, all in one go. Now this is a tabletop version. We're going to have a look at a few of the components they've got on show here. Now what I find fascinating is they're going from plastic, maybe additive or injection molded parts, some definitely additive parts here. They've got plastic injection molds, more additive stuff. And we're going from a low density all the way down here to a higher density. So we're going down to aluminium die cast, and then even a full alarm clock, and even an assembled headlight here. So why would you want to do an assembled headlight? That's because it might take a while to assemble this inside the automotive cell, and especially if you're doing some prototype production, you don't know maybe if the headlight is going to work until you put it in the car. Now it's quite a high cost if you assemble the whole thing, put it in the car, and then find out that it's not right. You're then going to have to disassemble it and find out which component's not working. But if you put that inside the CT scanner, you can see all the wiring, all the controls, all the contacts, all the electrical gubbins inside the headlight, and you don't have to disassemble it to see maybe there's a wire broken inside of that. So what I love is the fact that you can see, this has been a lamp that's been scanned here. You can even see inside the lamp, you can see the little wire filament there that is colored a different color because it's a different density. So you can have a fully assembled product, put it inside your CT scanner, you know exactly what is happening inside your product. This from Wenzel is a small. This is 100, let me check the voltage, it's 130 kilovolts. Now, with CT scanning, the volts dictate what the density of material you can penetrate is, and then the amps or the watts, well, the amps and the watts, the power, dictates how fast the cycle time can be. Now, this is 130 kilovolt, which is absolutely huge for a machine of this size. Normally, you won't be able to fit a machine of this size on a table like this. And the size that you can scan, let me grab this here. The size that you can scan is 83 millimeters by 46 millimeters high. Doesn't sound like much, but if you've got loads of medical parts, you've got sliding ahead parts, and you want to inspect all the internal features to a dimensional accuracy of 5 micron, you can do that with the CT scanner here. The reason it's so small, the space is so small, is because these need to be fully protected. This is a fully protected cabinet. If you imagine when you go to a dentist and you get your teeth x-ray scan, the dentist has to go outside and the nurse has to go outside because there's a little bit of an exposure to x-rays every time that happens. So they have to go outside. You only get exposed a little bit. But because this is fully protected, fully lead lined, they can be CT scanning, firing 130 kilovolts worth of x-rays onto a component here while people are walking around. Absolutely fine. So this is a super safe piece of kit that you can use to inspect density, geometrical accuracy. That's computer tomography, but it's really inspection. Check them out today. And we're back. The resin is just set now, Christina. What are we going to do next?
next we will remove the sample out of the mold.
We can pull it
and
out.
we can remove the
Yeah, the top cap.
top cap.
Yeah.
Yeah. And
Push it out.
Push it out, and there we have a perfect
Embedding. So the material is stuck in there now. Then,
Yes.
how do you turn it into this? Because what you want to do is put it in a machine
now
and
we
measure
will
this,
start,
right?
with grinding with silicon carbide paper, for example, with water cooling, and then we will polish it with different cloth and diamond suspension, and afterward we will etch it, and then we can find this inner structure of the material under the microscope.
Perfect. So it's going to get ground, etched, and then the inner structure will be found. You know your material integrity is good. You know your component is good. Your car is not going to fail. Your plane's not going to fail. That's how you do materials testing with Kulza samples. If you were listening to my presentation on the Wenzel stand pop quiz, do you know what CT stands for? You got it, it's computer tomography. Now that is 3D scanning of materials and components for dimensional accuracy and also the material integrity. Here on the Nikon stand, they've got a massive CT scanner. Now this is the largest scanning volume in a single cabinet design, and that combined with, down there they've got two guns here that pump out the X-rays. On the left-hand side you see the bigger one. Now that is 450 kilovolts, which is absolutely huge. It allows you to hit really dense materials such as Inconels, those nickel alloys, heat-resistant superalloys that you find in aerospace. This is so important for two things. The large scanning volume allows you to put kind of big automotive parts in. There might be carbon fiber or steel or stainless, or that might be additively manufactured that will have internal features, and also the nickel alloy additively manufactured parts that go in the hot end of turbines that will be additively manufactured as well, meaning you can check all those internal features that would previously be a big assembly where you could inspect every single component, put it together and it works. Instead, when you make it all, you've got no idea what a little coolant inlet tube size is. You need to put it on one of these machines. It's also good for those honeycomb structures and little carbon fiber walls inside automotive parts, and they're used a lot in F1 as well. Now, what Nikon love about this is the fact that it's all a complete cabinet. It's all one piece, and it weighs 20 tons, believe it or not. Because of the lead lining, that means it's completely protected. It means it's perfectly safe. While it's running, Andrew was telling me you could lean against it for a whole year. While it's running, you'd be absolutely fine. But because it's lead lined, 20 tons, but you can drop it in your machine shop as a single cabinet. No building up needed. There's a bit of commissioning, but not a huge amount, but it's almost plug and play that goes in your lab, in your machine shop for in-process inspection, or even once you're finished your final product, that big fat aerospace additive part, you can scan it with this one from Nikon. That's been Control Expo 2023. Thanks to the guys at ASOB, I got away home.